And as you know, ad hoc networks, which are sort of temporary networks, mobile networks, they are called MANETs, and that's why the name VANET, which is vehicular networks. One of the major communication technologies, I think, last about 10 years ago, is wave network, very short networks, communication networks. Here, sorry, I'll go back. Yeah. So the wireless access in vehicular networks, which are about 8 to 10 years ago, one of the standards used, pretty well standard. And the major components we classify in vehicular networks or VANETs are 3 of them: roadside units, which are sort of, the name implies they're next to the road, and onboard unit, which is in the car, it's inbuilt in the car. Application unit can be a sort of a service provider. It is whether it's optional, you can have it or not, depends on the applications. So they are the main components we classify, especially in VANETs. So if we say VANET, the main components here. And obviously, I think you must have heard in the news, Google started their own automated system vehicles. So it's also called driverless vehicles, and they trialed a couple of times. Some crashed, some did well. So it's still in trial. We're hoping in 1-2 years it's sort of a more stabilized outcome research, basically. The VANET, there are a lot of applications. Some you must have seen in your GPS already started to locate the petrol bunks nearby, and a lot of applications. But they actually classify into 2 broadly. I would say infotainment, which is like a entertainment applications, and safety applications, very important. I think these are one of the major applications now. BMW already implemented, Volkswagen, I think, and Mercedes-Benz actually implemented some of them, which is collision avoidance, which already implemented in BMW, if I'm right. Some public safety features also. And there is some vehicle in BMW, it's called energy efficient vehicle, where it actually tries to stop before the red light, sort of energy efficient. So some are already implemented, bits and pieces, but the whole package will be sort of ready by a couple of years, let's say 2 years, I think. What we meant here is basically the safety applications, as you know, very important is obstacle ahead. So there's some accidents or something on the road which is not visible. These indications are very important because that can cause a lot of crashes and sometimes death also. So very important applications here. But that's something else looking after, but that's not our paper here. Before we go to the paper, actually, I want to classify, just quickly brief you on communications. Vehicle communications are divided into 2-way communications: vehicle-to-vehicle communications, which is between the vehicles; vehicle-to-infrastructure, between the infrastructure and the vehicle, which is also roadside unit, you can call it. So something like this. You have a tower, mobile tower, or any other infrastructure which can communicate with the vehicle. That's called V2I. If it is between vehicle to vehicle, that's called V2V. Very simple. And they have their own dedicated, the channels and bandwidths, everything all standardized. Almost all the countries has standardized the communication channel. It's called dedicated short distance range communications. And this is the format they use. Pretty standard. I mean, these are all very well standardized. This one. So this is our work. Coming to our work, see what happens is there are a lot of communications between V2I and V2V. There are a lot of communications going on. It's like a big jungle. What happens is a lot of vehicles try to transmit messages. Okay? Either it can be V2V or V2I. The message aggregation is a process used to transmit minimal data. What happens is they may be same message. So it's trying to tell that there is an obstacle in the front, and 10 cars trying to send the same message, which is not efficient at all. Because imagine in a highway or freeway, hundreds of cars, and trying to send the same message again and again, or trying to merge together, it's not efficient. So our work is trying to standardize that, trying to make it a framework which can minimize the aggregation process. Aggregation process is divided into 3: decision phase, where you make a decision whether it's try to merge or not. A fusion where you actually merge the message, make it one, and then disseminate, means you spread the message. And it's very critical. It's not something VANET takes easy, because if it is a real safety message, you have to make sure it reaches the destination well in time. Otherwise, there's no point in here. So that's what we call delay, tolerant applications. The preventing the performance of vehicular networks and safeguarding the dissemination limit. So all our work regarding message aggregation has to converge into, we have to prevent life losses, basically, because if there is an accident in the front, obstacle in the front, it has to be, the message has to aggregate properly within time. So that's the thing. There are various schemes already available. There's a lot of work done. I mean, it's not pretty new, but what I'm highlighting here is there are disadvantages here, and I'll discuss about our work quickly. So there are other aggregation schemes there, but the issues with them, the schemes are lack of intelligent aggregation. There's no sort of formal, there's no standard where you can use that standard for aggregation. No classification of high dynamic environment, because sometimes the vehicles are, for example, freeway, you can go in 100 kilometers or 110 kilometers, high, very dynamic environment. So there is no classification there. Applications, there is no specific scheme for applications, and obviously redundancy is there. A lot of same messages are going through. That's one disadvantage. Less flexibility for critical information. So there is no flexibility for critical information. So these are the ones, and we want to identify some of them, especially redundancy. We want to sort of manage it more properly. So our proposal is to generalize framework for message aggregation and reduce the redundancy, as I said before. And we use a standard IEEE standard 1609.3, which is a standard. And we specifically use a one parameter at this stage, but we're going to expand further, process ID, and I'll show you how we did this one. We identified certain steps here to make it a framework to generalize this structure. We use infrastructure, providers, vehicles. Of course, infrastructure is a tower, something like a tower. Providers are, providers like your mobile providers or communication providers, and vehicles are your vehicles. We selected few applications for our purpose here. We collected some parameters and we categorized the parameters. I'll show you one by one there. And this is a sort of rough diagram. Sorry, it's pretty small, but if you can sort of, it's basically talking about the resources and applications. Applications, as I showed you before, there are safety applications and infotainment applications. We are more into safety applications. Infotainment is something like, it's like the entertainment. So that's sort of low priority, but our high priority is on safety. So this is the one. So we sort of mapped that safety applications here, especially collision avoidance, public safety, emergency braking, so on and so forth. Classify them, and we actually, the resources are basically the one which I described before. Some of the parameters I'll show you before again. Some of the resources are vehicles. Vehicles are resources. As you can see, the resources are responsible for feeding the data. These are the ones, they are the source of the data. They send messages like there is obstacle, there is some accident in the front. These are done by sensors. There are sensors on the car, installed on the car. So they will tell you whether there is obstacle or not. Okay. Infrastructure can be roadside units, RSUs. Your vehicle has, we assume that your vehicle has an onboard unit. It's sort of a small processor which processes some messages, very simple messages. Providers are some providers like your mobile providers. They are also providers for vehicular communications, like telecommunication companies. Our applications, as I said before, in this work we consider on the safety applications, especially collision avoidance, public safety, like crossing the signals. The human beings actually crossing the traffic lights, and other information like emergency vehicles and things like that, because they have the higher priority. So these are some of the applications. And we classify the parameters obviously both mandatory and non-mandatory. Means compulsory and non-compulsory. Compulsory are some parameters which are very important. We think you can't miss them. So they are the ones. And example are vehicle ID, vehicle position, TAMS time. Very important to identify a vehicle. The rest are sort of not necessary, but if you want to keep it, you can have them. So the frame structure using is sort of a language. We use a UML sort of unified model language to classify them using some parameters. You can see there. I mean, again, it's a very small slide, but if you see the complete paper, we found out there are some parameters we had used, compulsory and non-compulsory again, and we classified them. So we have a good structure here. So what we did is basically identified the RSU as the roadside unit, message, the class represent the mandatory parameters of the framework, which is in the previous slide. See the messages here. Message can be this type. Applications can be defined like this in this. I mean, I'm not sure whether you know the class language. These are classes. We define various classes based on the parameters also, and mandatory parameters and some information. But it's like trying to make it more structured. That's what we're trying to do. When the message is aggregated, we want to make sure all messages which are same has to be one, and then forward to the other vehicles. That's our whole this one. And one of the applications we looked at, as I said, one or two applications, and we identified one unique parameter, or this one, PSID, which is a process ID, and we use this provider ID. We use this as one of the sort of a example, and I'll show you one of the examples here. So we studied we took a case study. The vehicle's actually V2V, and it actually this is only V2V. They're trying to send messages to RSU and to the vehicles. So it is both V2I and V2V. What happens is here, when the RSU receives a message, RSU is roadside unit, it has the car IDs, so it will identify that car, and it also has the provider ID. Okay, these are unique IDs given by the protocols, and message ID. These messages IDs are defined. So, for example, 101 is collision avoidance. There is a collision. 102 is some message. Okay. So there is a list of messages, well defined, and they are actually stamped here. And the longitude and latitudes, the GPS coordinates are also given. So this is the captured snapshot and cars here. What we did is, based on PSID, again, make message aggregation. Based on PSID, we filtered the 3 to 4 one, this one, and try to see, because we're trying to find out in this task, we're trying to find out the nearest point to the collision, so that can distribute the message to other vehicles in the region, in the specific region. So here we filtered first with the PSID, the message which is 101, the particular provided ID, and found out these are the 3 cars which IDs are here, which has different longitude, different positions, and this is the nearest one. See longitude and latitude. So car ID 1034 with this message ID or PSID, it's message 101 is the nearest one to the collision. So there's something happened, and we found out that from here, from this big table, from the long list of messages, we're trying to find out, filter them based on specific parameter. Again, I'm not saying this is the best way, and you don't have to use PSID. There are other parameters, but this example is based on PSID. Okay. By doing this, you can cut down the lot of messages into, compress them, aggregate them, and then the message can be disseminated, based on instance, again, applications. So the GPS coordinates are used to field. Depends on your application. If you don't want the GPS coordinate, coordination. You can filter based on your nearest longitude, latitude. You can filter on messages. You can filter on IDs also if you know the IDs. So what we're trying to do is aggregate the messages, because there are so many messages coming through, and make a sort of a intelligent